MSc Chemistry, Physical Chemistry, Unit 2, Thermodynamics. Introduction to Laws of Thermodynamics. Thermodynamics is the flow of heat. First law of thermodynamics. The first law of thermodynamics states that energy can neither be created nor be destroyed, although it can be transformed from one form to another. This is also known as law of conservation of energy. Delta U is equal to Q plus W. Thus, whenever energy in one form disappears, an equal amount of energy in some other form must appear. It is known that energy can be produced by the destruction of mass, the two quantities being related by the expression E is equal to mc square, where E is the energy produced by the destruction of mass, m and c is the velocity of light. The modified law therefore states that the total mass and the energy of an isolated system remains unchanged. Internal energy and first law. And every substance is associated with a definite amount of energy which depends upon its chemical nature as well as upon its temperature, pressure and volume. This energy is known as internal energy U. Delta U is equal to UB minus UA. Delta U is equal to change in internal energy. UA and UB are the energies associated with the system in the states A and B respectively. Energy change accompanying a process is a function only of the initial and final states of the system and is independent of the path or the manner by which the change is brought about. Delta U is equal to UB minus UA is equal to Q minus W, where Q is equal to heat absorbed from the surroundings while undergoing change from state A to state B. W is equal to work performed, mechanical or electrical. In general, if in a given process the quantity of heat transferred from the surroundings to the system is Q and the work done in the process is W, then the change in internal energy delta U is given by delta U is equal to Q plus W, which is a mathematical statement of the first law of thermodynamics. If work is done by the surrounding on the system, as during the compression of a gas, W is taken as positive so that delta U is equal to Q plus W. If, however, work is done by the system on the surroundings, as during expansion of a gas, W is taken as negative so that delta U is equal to Q minus W. Del Q reversible is equal to du plus p dv. H is equal to u plus pv. Delta H is equal to qp. Delta H is equal to ncp delta t. Cp minus cv is equal to r. Second law of thermodynamics. Need for the second law. The first law tells us that the energy is conserved, but it doesn't tell us in which direction a process will occur. The second law has many equivalent statements, all expressing the same physical truth. Natural processes have a direction and are irreversible. A. Kelvin-Planck statement. It is impossible to construct an engine that operates in a cycle and converts all the heat absorbed from a heat reservoir into equivalent work without losing any heat to a cold reservoir. In other words, no heat engine is 100% efficient. Mathematically, neta is equal to 1 minus Q2 upon Q1 less than 1. Q1 is equal to heat absorbed from the reservoir. Q2 is equal to heat rejected to cold reservoir. Example, steam engine or Carnot engine. Clausius statement. It is impossible to construct a cyclic process whose sole effect is to transfer heat from a colder body to a hotter body without any external work. Heat cannot flow spontaneously from cold to hot. Example, refrigerator requires external work, electric energy to transfer heat from inside cold to outside hot. Concept of entropy. Entropy is a measure of disorder or randomness in a system. Mathematically, for a reversible process, ds is equal to delta q reversible upon t. For finite change, ds is equal to integration del q reversible upon t. Unit of entropy is equal to joule mole inverse Kelvin inverse. Physical meaning of entropy: higher disorder means higher entropy. Nature tends toward maximum entropy. Entropy change gives the direction of spontaneous change. S is equal to K ln W, Boltzmann entropy equation, where S is equal to entropy, K is equal to Boltzmann constant, W is equal to number of microstates ways energy can be arranged. If W increases, S increases. Greater disorder. Law of mass action developed by Goldberg and Weg. Statement: at constant temperature, the rate of a chemical reaction is directly proportional to the active masses, concentrations of the reactants, each raised to a power equal to its stoichiometric coefficient. For a general reaction, small a capital A plus small b capital B equilibrium, small c capital C plus small d capital D. The law of mass action gives the equilibrium constant. K is equal to concentration of equilibrium molar concentration of C raised to power its stoichiometric coefficient, equilibrium molar concentration of D raised to power its stoichiometric coefficient upon equilibrium molar concentration of A raised to power its stoichiometric coefficient into equilibrium molar concentration of B raised to power its stoichiometric coefficient, where A, B, C, D are the equilibrium molar concentrations and small a, small b, small d are their stoichiometric coefficients. Active mass means effective concentration. In dilute solution, active mass is equivalent to molar concentration. Why we use activities? According to rate law, K is equal to equilibrium molar concentration of the products raised to their stoichiometric coefficient upon equilibrium molar concentration of reactants raised to their stoichiometric coefficient. But modern thermodynamically correct form use activities AI instead of concentrations. This K is constant at a given temperature, independent of initial amounts, pressure, etc., and depends only on temperature. Concentration alone does not account for non-ideal interactions. Thermodynamics uses chemical potential mu I, which depends upon activity AI. Mu I is equal to mu I naught plus RT ln AI. Mu I naught is equal to chemical potential in standard state. AI is equal to activity dimensionless. For ideal solutions, AI is equivalent to Ci upon C naught. For ideal gases, AI is equivalent to Pi upon P naught. Using activities makes the law exact. K expressed in activities is a true thermodynamic constant. Thermodynamic derivation. The thermodynamic derivation of the law of mass action relies on the equality of chemical potential mu for all species in a system at equilibrium and the relationship between chemical potential and the Gibbs free energy change delta G naught. Consider the reaction small a into capital A plus small b into capital B equilibrium small c into capital C plus small d into capital D. Now, as we know that the total free energy of reactant Gr can be formulated as GR is equal to A mu A plus B mu B. Equation number 1, where mu A, mu B are the chemical potentials of reactant A and B respectively. Similarly, the total free energy of the product GP can be formulated, that is GP is equal to C mu C plus D mu D. Equation number 2, the temperature and pressure are kept constant. Moreover, the free energy change of the whole reaction can be obtained by subtracting equation second from first, that is del G reaction is equal to Gp minus Gr. Del G reaction is equal to C mu C plus D mu D minus A mu A plus B mu B. Equation number 3, the free energy change at equilibrium is 0. Equation 3 becomes C mu C plus D mu D minus A mu A plus B mu B is equal to 0. Equation number 4, as we know, mu I is equal to mu I naught plus RT ln Pi. Equation number 5, where mu I naught and Pi are the standard chemical potential of the species and partial pressure respectively. Equation 5, using equation 5 in equation 4, we get C multiplied by mu naught C plus RT ln Pc plus D multiplied by mu D naught plus RT ln Pd minus A multiplied by mu A naught plus RT ln Pa plus B multiplied by mu B naught plus RT ln Pb is equal to 0. C mu C naught plus CRT ln Pc plus D mu D naught plus DRT ln Pd minus A mu A naught minus ART ln Pa minus B mu naught B minus BRT ln Pb is equal to 0. C mu C naught plus RT ln Pc raised to power C plus D mu D naught plus RT ln Pd raised to power D minus A mu A naught minus RT ln Pa raised to power A minus B mu B naught minus RT ln Pb raised to power B is equal to 0. RT ln P C raised to power C plus RT ln Pd raised to power D minus RT ln Pa raised to power A minus RT ln Pb raised to power B is equal to minus C mu C naught plus D mu D naught minus A mu A naught minus B mu B naught is equal to RT ln Pc raised to power C Pd raised to power D minus Pa raised to power A Pb raised to power B is equal to minus C mu C naught plus D mu D naught minus A mu A naught minus B mu B naught is equal to RT ln Pc raised to power C Pd raised to power D upon Pa raised to power A P into Pb raised to power B is equal to minus del P naught minus del R naught, as Gp naught is equal to C mu C naught plus D mu D naught and Gr naught is equal to A mu A naught plus B mu B naught. Then RT ln Pc raised to power C Pd raised to power D Pa raised to power A Pb raised to power B is equal to minus del G naught reaction. Then del G naught reaction is equal to minus RT ln K, where K is equal to Pc into Pc raised to power C Pd raised to power D Pa raised to power A Pb raised to power B. Clausius-Clapeyron equation. The Clausius-Clapeyron equation is a thermodynamic equation that describes the rate of change of equilibrium vapor pressure with temperature during a phase transition. It relates the slope of the phase boundary in a PT diagram to the enthalpy change and volume change of the phase transition. In mathematical form, dp upon dt is equal to del h upon t delta v, where dp upon dt is equal to slope of phase equilibrium line, delta H is equal to molar enthalpy of phase transition, delta V is equal to change in molar volume during phase transition, T is equal to absolute temperature. This is the Clapeyron equation for liquid to vapor. Using ideal gas approximation, it becomes ln P is equal to minus delta H vaporization upon RT plus C. This specific form is called the Clausius-Clapeyron equation. Derivation. In order to derive the Clausius-Clapeyron equation, consider a system at equilibrium, that is the free energy change for the ongoing process is 0. That is delta G is equal to 0. Also, we note that dG is equal to VdP minus SdT. Equation number first. For typical single constituent, we have phase 1 in equilibrium with phase 2. Equation number 2. Where phase 1 can be solid, liquid or gas, whereas phase 2 can be liquid or vapor depending upon the nature of the transition, whether it is melting, vaporization or sublimation respectively. Now, consider a system at pressure P and temperature T, and the free energies of phase 1 and phase 2 of the same system are G1 and G2 respectively. Moreover, if we change the temperature from T to T plus dt and pressure from P to P plus dP, the free energy change in phase 1 and phase 2 will be dg1 and dg2 respectively. Mathematically, dg1 is equal to v1 dp minus s1 dt. Equation number 3, dg2 is equal to v2 dp minus s2 dt. Equation number 4, where v1 and s1 represent the molar volume and entropy of phase 1, while v2 and s2 represent the molar volume and entropy of phase 2. However, if the phase 1 and phase 2 are in equilibrium with each other, we have delta G is equal to 0, G2 minus G1 is equal to 0. Equation number 6. As G1 and G2 are free energies of the phase 1 and phase 2 at temperature T and pressure P, we can say that the same must also be true at temperature T plus Dt and pressure P plus Dp, that is G plus dG2 minus G1 plus dG1 is equal to 0. G2 minus G1 plus dG2 minus dG1 is equal to 0. Since G2 minus G1 is equal to 0, dG2 minus dG1 is equal to 0. dG2 is equal to dG1. Equation number 8. Putting values of dG1 and dG2 from equations 3rd and 4th, we get V2 dP minus S2 dt is equal to V1 dP minus S1 dt. Or V2 dP minus V1 dP is equal to S2 dt minus S1 dt. V2 minus V1 dP is equal to S2 minus S1 dt. Delta V dP is equal to delta S dt. dP upon dt is equal to delta S upon delta T. Equation number 9. Now, if the delta H is the latent heat of phase transformation occurring at temperature, the energy change is delta S is equal to delta H upon T. Putting this equation in equation 9, dP upon dt is equal to delta H upon T delta V. Equation number 10, Clapeyron equation. Now, if phase 1 is solid while phase 2 is vapor, that is solid equilibrium melt equilibria, the equation 10 becomes dP upon dt delta H fusion upon Tf delta V. Equation number 11, where delta H fusion is equal to latent heat of fusion, Tf is equal to melting point, delta V is equal to Vl minus Vs. For vaporization equilibrium, that is liquid in equilibrium with vapor, dP upon dt is equal to delta H vaporization upon Tb into Vv minus Vl, where delta H vaporization is the heat of vaporization and Tb is the boiling point. The term delta V is equal to Vv minus Vt, that is the difference in the volume of vapor and liquid phases. As the volume of the liquid is very small in comparison to the gaseous phase, the term Vl in the equation 12th can be neglected for simplicity. dP upon dt, delta H vaporization upon TVV. Equation number 13. If the vapor act as an ideal gas, that is PVV is equal to RT or VV is equal to RT upon P, then dP upon dt is equal to delta H vaporization upon RT square into P. 1 upon P into dP upon dt is equal to delta H vaporization upon RT. dP upon P is equal to delta H vaporization upon R into dt upon T square. On integrating, ln P is equal to minus delta H vaporization upon R into 1 upon T plus C. This is Clapeyron equation. Important results and interpretation. Vapor pressure increases exponentially with temperature. A plot of ln P versus 1 upon T is a straight line. Slope is equal to minus delta H vaporization upon R and intercept is constant. This method is used to determine enthalpy of vaporization experimentally. Applications of Clapeyron equation. First, determination of enthalpy of phase transition delta H. The equation allows us to calculate enthalpy of vaporization delta H vaporization, enthalpy of fusion, enthalpy of sublimation by measuring vapor pressures at 2 or more temperatures using ln P2 upon P1 is equal to minus delta H upon R into 1 upon T2 minus 1 upon T1. Second, if vapor pressure is known at one temperature, the equation can be used to find vapor pressure at different temperature. Third, the boiling point of liquid at any temperature can be determined if the boiling point at a particular temperature and latent heat of vaporization of the same are known. Fourth, Clapeyron explains why water boils at lower temperature on mountains, low pressure. Water boils at high temperature in a pressure cooker, high pressure, because ln P is directly proportional to minus 1 upon T. Higher pressure means higher boiling point and vice versa. Fifth, used to check if a phase transition will occur via compression or expansion in solid in equilibrium with melt equilibria. dP upon dt is equal to positive when expansion. dP minus dt is equal to negative then compression. Phase diagram for two completely miscible component systems gives phase rule states that F is equal to C minus P plus 2. Equation number first, where F is equal to number of degrees of freedom, C represents the number of components, P is equal to total number of phases. For a two-component system, the equation 1 reduces to F is equal to 2 minus P plus 2 is equal to 4 minus P. Equation number second. Types of two-component system based on number of phases. First, when we use P is equal to 1 in equation first, we get F is equal to 4 minus 3 is equal to 3. F is equal to 4 minus 1 is equal to 3. This means that for a one-phase and two-component system, there are 3 degrees of freedom. Hence, the 3 degrees of freedom can be depicted along the 3 axes of a cube. However, it is more common to vary only 2 variables while keeping the third one constant. Second, when we use P is equal to 2 in equation first, F is equal to 4 minus 2 is equal to 2. Third, when we use P is equal to 3 in equation number first, F is equal to 4 minus 3 is equal to 1. Therefore, we can conclude that the number of degree of freedom in such condensed system is actually reduced by 1, that is F dash is equal to C minus P plus 1. Types of completely miscible two-component system in solid-liquid equilibria. First, eutectic system. In these type of systems, the components do not react with each other, but only the simple mixing takes place in the solution or in the molten state. Phase diagram of eutectic systems. Second, system forming solid compounds AX By with congruent and incongruent melting point. In these type of systems, the components do react with each other and the formation of a compound takes place. Common example is magnesium zinc system. System forming solid compounds with congruent melting point. In these types of system, the two components react to give a compound which is quite stable, and until its melting point is reached. When melted, the composition remains the same as that of the solid. Example: magnesium, zinc and FeCl3 water system. System forming solid compounds with incongruent melting point. In these types of systems, the two components react to give a compound which is not stable up to its melting point. When heated, the decomposition starts before the melting point is reached, and a new solid phase in a solution or melt with a different composition from the original solid are formed. Such compounds are said to be undergo pre-tectic or transition reaction are labeled to have a congruent melting point. Example: Na2SO4 and water, and NaCl and water system. General phase diagram for systems forming solid compounds with incongruent melting points. Third, system forming solid solutions. In these types of system, the components are completely miscible with each other in solid phase, and completely homogeneous solid solutions are produced. Calculation of eutectic point. If the composition of the solid mixture in which compound A is 80° while compound B is 20°, represented by vertical line X, therefore it follows the above mentioned rule that after crystallization we must get the same composition, that is 80% solid A plus 20% solid B. Now if the system allowed to cool down and then the temperatures are plotted, it will cool down very rapidly in going from point X to point 1. However, point 1, the crystalline of compound A will also start releasing a large amount of heat, and therefore the rate of cooling will be slow until point Q is reached. Now, since the system is getting solidified at eutectic temperature, that is, it is moving from Q to Q dash, the temperature of the system will remain constant during this conversion. At point Q dash, both compounds will exist as solids, and therefore the system will cool down below point Q dash. Along the vertical line X, the same type of curve will be obtained if we start from composition left to the eutectic composition. The only difference will be that the compound B will separate out first up to point Q, and then the solidification of compound will start. Phase diagram of thermodynamic treatment of solid solutions. The general thermodynamic treatment of solid solutions include the shift in the solvent's freezing point during the crystallization and the nature of the cooling curve, as well the necessary discussion on both concepts in given below. First, the shifting of solvent's freezing point during crystallization. The thermodynamic expression for the shift of solvent's freezing point when the solid begins to solidify during cooling can be obtained by assuming the solid solution as an ideal solution. Therefore, the chemical potential for ith constituent mu I can be given by the following relation. Mu I is equal to mu I naught plus RT ln Xi. First equation. Xi represents the fractional composition of the constituent, where mu I is the chemical potential of the pure solid. After setting the primary condition for the phase equilibrium between solid and liquid, we have mu I as in equilibrium with mu 1 L. Equation number second. Considering both as ideal, we can write above equation using equation first. Mu I naught S plus RT ln X1 S is equal to mu I naught L plus RT ln XIL. Equation number third. After rearranging, we get RT ln X1S minus RT ln X1L is equal to mu I naught L minus mu I naught S. Equation number 4. RT multiplied by ln X1 S minus ln X1 L is equal to mu I naught L minus mu I naught S. Equation number 5. R ln XIS upon XIL is equal to mu I L minus mu I naught L minus mu 1 naught S upon T. Equation number 6. Now since mu 1 naught L minus mu1 naught S represents the molar free energy of the fusion for the pure solvent at pressure P and temperature T. The equation can also be written as R ln x1 S upon x1 L is equal to delta fusion mu1 naught upon T. Equation number 7. Putting the values of molar free energy of fusion delta H delta fusion mu1 naught is equal to delta fusion H naught 1 comma m minus T delta fusion S 1 naught m. In the above equation we get R ln x2s upon x1l is equal to delta H naught fusion 1 comma n minus delta T delta S fusion naught 1 comma m upon T. R ln x1s minus x1l is equal to delta fusion H naught 1 comma m upon T minus delta fusion S naught 1 comma m. Equation number 8. Recalling the entropy of fusion at for the pure solvent at the temperature T1 naught melting point, that is delta S naught fusion 1 comma m is equal to delta H naught fusion upon T1 naught. Using the above result in equation 8, we get R ln x1s upon x1l is equal to delta H naught fusion upon T minus delta H naught fusion upon T1 naught. R ln x1s upon x1l is equal to delta H naught fusion into T1 upon T minus 1 upon T naught. R ln x1s upon x2l is equal to delta H naught fusion into T1 naught minus T upon T1 naught. After putting T minus T1 naught is equal to delta Tf, the above equation takes the form R ln x1 x upon x1l is equal to delta H naught fusion into minus delta Tf upon Tt1 naught. If the solution is very dilute, the melting point T1 naught will be quite close to the temperature T. Therefore, Tti1 naught can be replaced by T1 naught square. Therefore, equation 11th takes the form R into ln x1 S minus ln x1 L is equal to delta H naught fusion into minus delta Tf upon T1 naught square. Furthermore, for very dilute solutions, we have ln x1s is equal to ln 1 minus x2s equivalent to x2s. ln x1l is equal to ln 1 minus x2l x minus x2l. R minus x2s plus x2l is equal to delta H naught fusion into minus delta Tf upon T1 naught square is equal to minus Tf is equal to RT1 naught square upon delta H fusion naught x2 into L 1 minus x2s upon x2l. Recalling the expression for molarity, that is x2l is equal to n2l upon n1l plus n2l is equivalent to n2l upon n1l is equal to n2l upon small m1l upon m1 n is equal to n2l upon m1l into capital M1 is equal to small m into capital M1. Using above result in equation 13th, we get minus T delta F is equal to RT1 naught square into M1 upon delta H naught fusion into m into 1 minus x2s upon x2l is equal to delta Tf is equal to minus kfm into 1 minus k. K is equal to distribution coefficient given by x2s upon x2l. If delta Tf can be negative or positive depending upon the magnitude of K. The nature of cooling curve of the solid solution. Now, because the two components of a solid solution can be completely miscible with each other, the maximum number of phases which can coexist is only 2. Therefore, recalling reduced phase f dash is equal to C minus P plus 1 first. After putting C is equal to 2 and P is equal to 2, we get F dash is equal to 2 minus 2 plus 1 is equal to 1. Equation number second, which means that there is only 1 degree of freedom. In other words, only one variable is needed to define the system completely, which can either be temperature or the composition.